In this video, I want to talk about the relationship between voltage and distance and electric field. So let's derive a little equation here, right? Let's start off with the definition of voltage. Voltage is the change in potential energy divided by charge, right? That's the definition of it. It could also be the work I do on a charge. We'll take a positive charge, say, from this plate here, from one potential to another potential. There must exist some change in voltage, right, between these plates for there to be a positive charge on this side and a negative charge on that one, okay? So if I take a positive charge and I move it through this distance, right, I'm doing work on it, and that's the potential energy it gains, right? So it's going to be the work divided by the charge. Well, work is just force times distance, and here I'm using x, delta x as a distance because they use it in the formula for some reason, right? So delta x, okay, divided by q, right? And now we can be even more clever about this force because there's a relationship. The electric field is also, what is it? It's force divided by charge. We know this, right? So therefore, force is E times Q. So we can substitute that guy in for force, right? So we have E electric field times Q times delta X over Q. So the Q's go away, and you get that the change in voltage is the electric field times the change in X. And that's assuming if X is large, that means that E has to be uniform for that, right? And then if I divide, I get that E is V over X, like this. And then the question is, why is there a minus sign? Well, technically I did this kind of back of the envelope. There really is a minus sign. I'll show you why. Okay, if you look at this thing, the electric field is to the right, okay, and the change in voltage is positive this way, and the delta x is positive this way, right? And so you got to put the minus sign there because the electric field is to the right, but the change in voltage and the delta x is to the left, right? I mean, the change in voltage is a scalar, right? But delta x is to the left, right? So the minus sign there is to reconcile that. Generally, I ignore it because anything, I mean, I know that if I move positive charge from this side to this side, I'm doing positive work and vice versa, okay? So I don't need the minus sign. And usually I ignore it, but sometimes I don't. Okay, I'll show you when I do, but usually I ignore that, okay, because I can figure out from the picture what's going on better than I can by trying to keep track of the minus signs there, okay? So let's look at an example here, right? What's the electric field when you have a 12 volts across two parallel plates? It's like a capacitor separated by 1.5 centimeters, right? Well, the electric field is negative delta V over delta X, right? So let's just draw this here. Let's go, let's suppose that we move it. Oh, I don't know, I'm not even going to worry about the minus sign. I'm just going to divide. So let's go 12 volts over point. I don't use the minus sign because I don't understand it now. I'm just kidding. I do. 12 divided by 0.015. 800, yay. Right? Notice that the units that we get are volts. This is meters, right? Volts per meter, right? You can say that it's also the same as 800 newtons per coulomb. The electric field equals both of these things, okay? That means that a volt per meter must be a newton per coulomb, but how? Okay, let's figure it out. This is the great mystery of our time. A volt is a joule per coulomb. And so a volt per meter is a joule per meter coulomb. And a joule is a newton meter. Ooh, that's cool. Newtons times meters, right? Because it's force times distance makes work over a meter coulomb. Yay, so that is a joule is a newton per coulomb. Now, having said that, volts per meter is a far more common measure of electric field simply because we make electric fields in particle accelerators and TV sets, old TV sets like cathode ray tubes and stuff, using parallel plates like this. We simply apply a voltage across a distance, and if you divide, you get the electric field. Moving the plates together makes the electric field stronger, apart weaker. Making the voltage bigger makes the electric field bigger, etc., etc. I'll come up with some useful analogies in class for that.